David Van Vranken. Welcome to the 22nd lecture in the Organic Chemistry 51C lecture series here at UC Irvine. We've been talking about the chemistry of amines, and this gives us the perfect opportunity to head over to the EROWID website. If you type the word EROWID into your internet browser, it'll lead you to a website called EROWID, created by Fire and Earth back in the 1990s. And when you look at the website, it looks like all kind of plant and botanical and mysticism. But let's look over here at the right side of the page, because that's where the interesting stuff is if you're an organic chemist like me, because this is the part that really highlights the work of Alexander and Anne Shulgin, probably through 3 or 4 decades of work. And the website introduces you to a book called PiHKAL. And PiHKAL is an acronym that stands for Phenethylamines I Have Known and Loved. Let's go ahead and talk about phenethylamines. Phenethylamines are a group of compounds characterized by a phenyl and an ethyl group, CH2CH2, attached to an amine that is basic and easily protonated. And you are probably familiar with many of the amines on this page. So let's take a look at some of these phenethylamines. I think the parent and most common member of this class is methamphetamine, also known as speed, sold as Adderall for various different types of issues. You may also know the compound Sudafed, sold in grocery stores over the counter for the treatment of allergy symptoms. The chemical name would be pseudoephedrine. I didn't show the stereochemistry here, but you can see embedded within it is the key structure of methamphetamine. And all you need is palladium on carbon and a tank of hydrogen gas, and you can easily cleanly remove that hydroxyl group and convert that into methamphetamine. Back in the 1990s, there was a kind of a craze for this thing called the fen-phen diet pill, composed of 2 phenethylamines, basically analogs of methamphetamine. One was phentermine, the other was fenfluramine. I didn't show that structure here. I think we've already mentioned mescaline. It's the hallucinogenic compound that you find in peyote cactus buds, and you can see the phenethylamine group in here with some methoxy groups on the arene ring. If you like to chew cat, maybe in the Middle East, it contains this compound called cathinone, which is a phenethylamine with a keto group on there. Also, another compound that is a phenethylamine in disguise is methylphenidate, sold commercially as Ritalin, or I think attention deficit disorder or some kind of, just to help you focus your attention. Ecstasy is a super popular variant of methamphetamine where they've added this methylene dioxy ring here. This methylene dioxy group, it's MDMA, methylene dioxy, methamphetamine. And compounds, some of these designer drugs have names like ecstasy. Here's one called Serenity that has 2 methoxy groups and a methyl group spaced appropriately on the arene ring. And these compounds were popularized by this book by Alexander Shulgin. And you can find the details of these compounds over here on the EROWID website. Skip all this other stuff and cruise over here to the section called Chemicals, into the Chemicals Vault, and then click on any of these compound names. And let's go ahead and explore the chemistry of phenethylamine derivatives. And when I hear phenethylamine derivatives, the reaction that comes to mind, there is a reaction that comes to mind called the Henry reaction. So this gives us an excuse to talk about a variant of the aldol reaction that is very efficient for constructing phenethylamine frameworks. So the Henry reaction is a variant of the aldol reaction where you use ammonia, and you're not using a ketone or an aldehyde to do the carbon-carbon bond forming step. You're using a nitroalkane, typically nitromethane or nitroethane. And these compounds are so acidic. They have a pK of about 10. So kind of on the order of a 1,3-dicarbonyl compound, that acidic. And if you'll note the conditions here, it's not simply throwing in ammonia as a base. Notice that they're adding acetic acid. Those are conditions for ammonium ion formation. Actually, you throw in the salt ammonium acetate. It's a mixture of amine and acetic acid. And what's happening in this reaction is you're generating a small intermediate amount of this ammonium ion. And ammonium ions are so reactive So at the same time that you're generating ammonium ions using the ammonium acetate that's present in there, you're also generating a small amount of this nitromethane anion that is super nucleophilic on carbon. And this ammonium ion is more reactive than the aldehyde starting material. It's more reactive as a Michael acceptor than this nitrostyrene product. And so the nitromethane anion attacks the ammonium ion and forms the key carbon-carbon bond. Under the conditions of the reaction, you have conjugate acids, conjugate bases floating around. So, right, of course, with acetic acid in there, it's easy to protonate the amine to make an ammonium ion leaving group. It's also easy to deprotonate the nitroalkane, just as easy as it was in the beginning. So you get an E1CB elimination that constructs this nitroalkene functional group. And one of the reactions that we did not tell you about is that lithium aluminum hydride is great for reduction of these nitroalkenes all the way down to an ethylamine group. And that's how you make phenethylamine. This is how Shulgin and other chemists before him made lots and lots of phenethylamine derivatives. This particular one is known as 2CT2, is the abbreviation. And what was amazing about the PiHKAL book is not only did it describe and give you robust chemical procedures for synthesis of these compounds, but Alexander and Anne and their friends took these compounds and described their experiences. So here's a description of what happens when one of that group took 22 milligrams of 2CT2. A slow onset, very vivid fantasy images, eyes closed but no blurring of lines between reality and fantasy. Some yellow-gray patterns a la psilocybin, that's the active ingredient in magic mushrooms. Erotic, lovely, good material for unknown number of possible uses, can explore for a long time. And that's PiHKAL. When we left off, we were talking about how to make primary amines by doing SN2 type chemistry. And we told you that you can't just throw amines and do SN2 reactions. You get over-alkylation typically. So I showed you this Gabriel synthesis for adding NH2 groups. It's kind of a roundabout two-step way to add an NH2 group through, if you really feel like you have to do an SN2 substitution reaction. Let me show you some other ways to synthesize amines, to form carbon-nitrogen bonds, to reduce groups down to amino groups, and let's see what that's about. So back in the section on electrophilic aromatic substitution, we taught you how to add nitro groups to benzene rings. You know, nitric acid and sulfuric acid, it generates a really aggressive nitronium ion. And then we showed you some chemistry for reduction of those nitro groups to anilines. And the conditions are super simple here. Generally, it's hydrogen and palladium on carbon. It's just a catalytic amount of that, a pinch of that black dust that you buy, palladium coated on carbon, charcoal-like carbon. And this is a great reaction because the only byproduct is water, so you just evaporate everything and you're done. And it's so clean, filter, evaporate, and you got clean aniline compounds. This is a great reaction. And the only disadvantage of this reaction is that it cleaves carbon-halogen bonds from your arene ring. So if you were in that situation, there's another set of methods that the book tells you to use to reduce nitro groups. And that's to use either iron or tin in the presence of acid. And I didn't really tell you about the iron. I'm not going to expect you to know that. Why would they tell you two methods and not tell you any advantage between them? I would say just remember the tin one. I'm not going to ask you about the iron method. So you take tin metal, some low-valent tin species, tin metal, and we do this in the presence of hydrochloric acid. So tin metal and hydrochloric acid, you throw in some tin powder, stir it around with hydrochloric acid. These are strongly acidic conditions. You're not going to get a basic amine out of this. It's going to be protonated by the hydrochloric acid that you're stewing this around in. So what you end up generating in this reaction mixture is going to be an anilinium chloride salt, a protonated form of aniline. And if you want the free amine, you have to follow that up with a sodium hydroxide workup, with a basic workup. You can just write sodium hydroxide. That's what you have to do. If you want to generate an aniline and then use that to make amide bonds or make imines out of that, then you've got to neutralize that. You've got to deprotonate it using sodium hydroxide. So it's 2 steps if you use this tin hydrochloric acid procedure. So how would you do that? If I asked you how to make this compound over here, and this looks to me like somebody put this nitro group on using electrophilic aromatic substitution. How would you do this 2-step procedure? Well, it's more common to enumerate these steps like this. We don't usually write out the intermediate, but I expect you to know that you're getting an anilinium, a protonated aniline, as an intermediate here. So you have to follow this up with something to convert that using base. And again, if you don't write the sodium hydroxide, you would not get this aniline, and you wouldn't be able to use this then for the next step if you wanted to use that nitrogen atom as a nucleophile. So the intermediate that you generate if you don't add the sodium hydroxide is this protonated aniline species. So just remember that when you're stirring amines around in hydrochloric acid, they're protonated. they're not sitting there in the basic form. And that's what the sodium hydroxide would do. All right, so it's super easy to add nitro groups to benzene rings, and it's super easy to reduce them. You've already learned this reaction. There's nothing new to learn here. This is just a review. We're kind of reviewing some of the methods that you know about to make amines. Okay, let's go ahead and talk about this reaction that you learned about when we talked about this in chapter 20 of the Gorzynski-Smith textbook, the 5th edition. There's this reaction here where you can take amides, and you know how to make amides now. We learned in chapter 22 that if you take an amine and a carboxylic acid and add DCC, you can make an amide. If you take an acid chloride and an amine, you have to have a base like triethylamine to soak up HCl. It's so easy to make the amide in virtually quantitative yield. And now the key thing is that we can reduce these carbonyl groups using a very simple process, lithium aluminum hydride, and then an aqueous workup. So easy. That is total money. This sequence of making an amide, which almost always occurs in nearly quantitative yield, and then doing this highly efficient reduction of the carbonyl to a CH2 group. I'm just gonna write the word money here. Oh my gosh, that is such a useful transformation. It's hard for me to imagine that I would have a final exam where that wouldn't be useful in some way, because it's such a common sequence, this idea of making an amide and then reducing it down to a CH2. That's how they put the methyl group on methamphetamine. If you make methamphetamine in the lab this weekend, you're probably going to be doing a lithium aluminum hydride workup on an amide to install that N-methyl group on methamphetamine. So if I ask you how you would do this, steps and reagents, starting from dimethylamine, don't try to do an SN2 reaction. That is not the way to try to make this bond here. I already told you, if you added propyl bromide, it would keep alkylating over and over again until you had a mixture of monopropyl, dipropyl quaternary ammonium salt, right? It's not, you can't just throw in an alkylating agent and do SN2 here. So how would you make this? What I would do is I would recognize the fact, let me draw this in a brilliant purple color here. I recognize the fact that that's got a CH2 group on it. So, wow, that means I could have made that through a reduction. So the way to do this is you first make an amide bond. Super efficient. How would we make this amide bond with a carbonyl there? Well, that's easy. We got a lot of different variants of this. Let me show you a conceptually easy one. I just throw in the carboxylic acid and DCC. I've got an amine, I've got a carboxylic acid, and I've got DCC. It's going to make that amide bond very efficiently. And then we come along and we do a lithium aluminum hydride workup or reduction. So lithium aluminum hydride, step 2, aqueous workup. I guess I normally write these out as Roman numerals. Let me do that. I usually just write the Arabic numerals if the intention is to isolate the intermediates. You don't have to be strict about that. So H2O workup. Wow, look at that. Right? If I see a CH2 group attached to a nitrogen, I'm thinking I could have made that using a lithium aluminum hydride reduction of an amide that was made through any number of different amide bond forming reactions, acid chlorides plus amines, DCC couplings. Money, man, that is money. I hope you guys remember that. That is so useful. I get so excited when we cover reactions that are actually really useful in the laboratory. All right, don't get overzealous on this. We showed you these reactions called the Wolff-Kieschner reduction and the Clemenson reduction for reducing ketones. Really, this is for ketones, reducing ketones to CH2 groups. And so let me just remind you of what some of those procedures are. One procedure is the Wolff-Kieschner conditions, strongly basic conditions, hydrazine, sodium hydroxide. And you heat the heck out of that. 100 degrees, you boil it in base. My gosh, those conditions are harsh. Or we could come along and do the Clemenson version of this, where we use zinc mercury amalgam. So zinc powder that's got a slight coating of mercury on there that kind of bonds with the zinc. Hydrochloric acid, these are strongly acidic conditions. You're either going to do this type of reduction under strongly basic or strongly acidic conditions. And in this case, it doesn't matter because there's nothing that would get destroyed or eliminated or ionized under these. You could take your pick here. But these conditions are really just for ketones. Nobody would really employ this with aldehydes. I guess in theory you could, but that's not really what it would be. It's a ketone for ketones. You might have this tendency, I'm not sure how to caution you against this, to say, to be confronted with this type of transformation and say, gee, how am I going to do this? If I asked you how to convert this amide to this CH2 group, I hope you're not thinking Clemenson reduction or Wolff-Kieschner reduction, because that's for ketones only. If you want to reduce this is that lithium aluminum hydride thing. Do not do, right? This you would do with lithium aluminum hydride. And step 2, aqueous workup. What would happen if you did try to do a Clemenson reduction or the Wolff-Kieschner reduction? So for example, it doesn't really matter at all whether I've got the hydrazine in there, but if you've got sodium hydroxide and you're boiling amides in high-powered basic conditions with sodium, the only thing you're going to get is amide hydrolysis, which is clearly not what you want if you're trying to keep that bond there. All right, you'd get this, and then sodium plus, and then you'd end up with your amine just sitting there unconnected, right? I hope these are kind of separated enough where you can see what's going on here. But don't use Clemenson reduction or Wolff-Kieschner reductions for amides or esters. They'll just hydrolyze amide or the ester. That's where you have to use lithium aluminum hydride to reduce down carbonyls. You get amide hydrolysis with those types of conditions. Boy, amines, so common in pharmaceuticals, so common in illegal drugs, so common in organic synthesis. It's one of the amines are such a common functional group. Now, we talked about nitriles a bit when we got to the chapter in 2 places. In the chapter where we were talking about organometallic reagents like Grignard reagents and hydrido addition reagents, we gave you this reaction that turns out to be pretty useful. And that is the reduction of this carbon-nitrogen triple bond of a nitrile. We can reduce those to CH2 and H2 groups. So see this carbon right here? That gets reduced down to this CH2 group right here. So that carbon in the end gets an NH2, and it's the same lithium aluminum hydride conditions that we use to reduce amides and esters, or ketones and aldehydes. But lithium aluminum hydride and aqueous workup. Very simple. So anytime I see a CH2 next to an NH2, I'm thinking, well, I could have reduced a nitrile group to to get to that. Why is that important? Because it's very easy to add nitrile groups. There's cyanohydrin formation reactions. There's also SN2 reactions where if you take sodium cyanide and just do an SN2, you could add a cyanide group and then reduce it down. And that process adds an extra carbon and an extra nitrogen. And after the reduction, you've got an extra CH2 and an NH2. I expect you to know how to use that process. If I say, I want you to do this transformation using any steps and any reagents that you want, you need to recognize that there's an extra carbon atom that got added there. And this is a great example of where you would use this two-step process of doing an SN2 reaction with cyanide followed by a reduction. So what would we do here? If we wanted to add an extra carbon, it's very easy to add an extra carbon atom. Boy, that's so easy. Sodium cyanide. Boy, cyanide anion is so slim and so trim. It's great for SN2 reactions. And then we come along here and we do our reduction process. Step 1, lithium aluminum hydride. Step 2, aqueous workup. So easy. Wow, that works so well. The yields are so high yielding. Right? And as soon as I make this amine, I feel like I want to make an amide, do a DCC coupling, or use it for imine formation, or any number of things that it's so useful for doing. Look, we're making a phenethylamine here. I suppose you could maybe use this as if you had the 3-methoxy groups, you could make mescaline out of that. That's not the standard route to use the Henry reaction. Oh man, awesome. So this reaction does so much stuff, I feel like. It forms a carbon-nitrogen bond, and it also leads to reduction at the same time. So when I see this group right here, I'm thinking a couple of things. I'm thinking, well, I could have made this bond here through first forming an amide and then doing a lithium aluminum hydride reduction. That's what I'm thinking. It's so easy. I could have, if I needed to make this, I could have made this by making an amide and then doing this reduction process. But you can't use that process for this isopropyl group because the isopropyl group doesn't have a CH2 next to the nitrogen. And so how would you make this other carbon-nitrogen bond? Not SN2. You're not going to be doing any SN2 to get this carbon. There's a great reaction we have for doing that, and it's called a reductive amination. It's this phrase right here. And we use this secret reagent that I don't think you have seen before called sodium cyanoborohydride. Wow, what a cool reagent. I'm not sure if I've drawn that reagent anywhere, but I just want to make sure let's go ahead and talk about this reagent. The way you write out that reagent is you write sodium, and this is a little bit disappointing, but well, I'll go ahead and draw it like this. Let me draw it the way it's commonly drawn. Sodium cyanoborohydride, CnBH3. God, that annoys me. CnBH3. That's supposed to be a BH3. What is that thing? Here's why it annoys me. Let me go over here and draw out the structure of sodium cyanoborohydride. You already know the structure of sodium borohydride. Sodium borohydride has 4 hydrido groups on that boron, and those bonds are nucleophilic. But sodium cyanoborohydride, some very clever person figured out, you know, if I put a cyano group on there that's electron withdrawing, these hydrido groups they lose their powerful nucleophilicity. And this reagent does not add, the hydrido groups do not add rapidly to carbonyls anymore. But what do they do? When you mix an amine, a secondary amine with a carbonyl, it forms Ammonium ions. There's a 5-step mechanism. I'm not going to draw the 5 steps for Ammonium ion formation. You already know those 5 steps. All right, 1, 2, 3, 4, 5. And it's in equilibrium. You'll end up, this is the basis of the Henry reaction. You're throwing ammonium acetate with an aldehyde, you generate Ammonium ions. And Ammonium ions are more reactive on this carbonyl type carbon down here. They're more reactive than aldehydes. You couldn't possibly have known that because nitrogen is not as electronegative as oxygen. But when you put the positive charge, it actually turns out that this is easier to attack on the carbon atom down here. It's easier to attack than a carbonyl group. So sodium cyanoborohydride is very choosy. It will selectively react with the small amount of Ammonium ion that's present. Small amounts. Even though most of your carbonyl compound is sitting around as the carbonyl, as soon as you generate small amounts of this Ammonium ion, it will then undergo reduction. The hydrido group comes in and reacts. So let me go ahead and draw it, kind of that arrow pushing. It's so choosy, just won't add to carbonyl groups. There we go, that's that This is why it annoys me, this classical way that we write out sodium cyanoborohydride. Is this normal way we write it out makes it look like the nitrogen is attached to boron. That bugs me, but that's what everybody does. So you've got these hydrido-boron bonds that are kind of nucleophilic, kind of choosy. They don't attack the carbonyl, but they attack the small amount of Ammonium ion that's present. That's super reactive. That's the way organic chemists do modern organic chemistry. You look at a whole host of reactions that we do where you think an aldehyde is reacting, but they've actually thrown in secondary amines in a lot of cases in order to generate small amounts of Ammonium ions, because those are so easy to attack. Okay, this is called reductive amination. You take a ketone, you take an amine, and it has to be, it has to have at least one H on there, right? There's at least one H. And you can kind of staple these two things together. So what's attached on here? What's attached on here, you get two new bonds. Here's one of the new bonds. It's the carbon-nitrogen bond. But there's another new bond that's on here. And that's the CH bond. Those are the two new bonds that you generate. Let me go ahead and highlight those. That's what a reductive amination does. Generates two new bonds at the same time. And you've got to look for that. Come back over here. There were two new bonds that were generated. So these are the new bonds. Here's one of the new bonds, and there's the other new bond. That wasn't, neither of those were there before. It used to be a carbonyl group. New and new. New bonds. And you have to practice that. You have to go to the back of the book and work problem after problem until you're good at seeing these disconnections. There is no substitute for that. You can't look at the notes and say, I understand the concept. Now I'm ready for the exam. You won't be. You have to practice it with 1,500 functional groups on there, and then you'll really be good at recognizing that disconnection as an option when you see it. It just takes practice. There's no short way around that. Now I mentioned before when I introduced this new area in chapter 25 of amines that you have to consider two possible reactions of amines. Amines can serve as bases. Amines are basic. They're not as basic as hydroxide anion, but they're basic. We use triethylamine all the time in the lab, usually to soak up acids, but sometimes to pull protons off. And amines are nucleophilic. So if you want to generate quaternary ammonium compounds, right, you can take a tertiary amine and do an SN2 reaction. So these are the reactions that we have to keep in mind. You know, first of all, this very fast and reversible acid-base process, so fast for amines to protonate. And then the reverse is also usually very facile, back and forth. And this equilibrium depends on the relative acidity of the ammonium ion and the relative acidity of the acid. When you're in an organic reaction that's not buffered, you're simply mixing together two species, you look at the two acids, and the difference in pKa's tells you the equilibrium. If the pKa's of these two species, right, this is, in these conditions, these are the two acids. This has a pKa of about, for most typical amines, about 10 to 11. It's like 10.5, so I'm never sure whether to use 10 or 11. If you know the pK of this one, right, if it's 100, if it's 2 orders of magnitude more acidic, then the equilibrium is 10 to the 2 to 1, 100 to 1. It's not hard to figure out where the equilibrium lies, and you establish that equilibrium very quickly. The nucleophilicity thing, that's typically slow. You typically do not generate equilibrium here. You go irreversibly, usually, under most of the conditions that we cover in 51C, you assume it's irreversible. I wish I'd drawn that in red because I kind of tend to favor red marks for the curved arrows for arrow pushing mechanisms. These are usually irreversible under the conditions that we talk about in chemistry 51C. There are cases where you can pop the alkyl group back off, but we usually don't talk about those conditions in this class. So I expect you to understand what's the relative reactivity of nitrogen lone pairs versus other types of lone pairs. You can usually guess, if all else is equal, you can guess the relative basicity or nucleophilicity just by understanding electronegativity. Let me go ahead and draw out a little portion of the periodic table here up on the top of our page. Periodic table in the second row is boron, carbon, nitrogen, oxygen, and fluorine. I just remember here that the carbon has an electronegativity of 2.5, and all the others fall in line. So 2.5, 3.0, 3.5, 4.0, all these second row atoms are about the same size. The only thing different about these is they have an increasing number of protons in the nucleus, and so they're different in how much they like having the electrons there. If we look at the relative reactivity of these lone pairs for these four types of atoms, an alkyl group has no lone pairs, right? If it's a neutral carbon, there's no lone pairs on there. So I'm not even going to consider that. But when we think about the relative reactivity of nitrogen, oxygen, fluorine, fluorine's electronegative. It wants those electrons. It doesn't want to share them. So it's the least reactive lone pairs of this group. Oxygen is more electronegative than nitrogen. So it doesn't want to use those electrons. Water is not this super powerful nucleophile. Maybe for attacking carbocations, it's okay. But amines are actually more reactive than any of these other two types. Amines are more reactive as bases, way more reactive as bases than either of these two, and more reactive as nucleophiles. If we consider the anionic forms of these four elements, it's the same trend. Now we can consider carbon, because you can have an anionic form of carbon that has a lone pair. And again, fluoride is electronegative. It's happy with the electrons. It doesn't want to share them by attacking something. So you'll find the same order of acidity and basicity. So acidity and basicity goes in this direction, or sorry, basicity and nucleophilicity. What am I? Basicity and nucleophilicity usually parallel each other. Nucleophilicity. I don't have room there. And it's the same over here, basicity and nucleophilicity. Carbanions are way more reactive than amide anions, and amide anions are way more reactive than alkoxides, and alkoxides are way more reactive than fluoride anions. We typically don't use fluoride anions very much in organic chemistry. Maybe when you go to the pharmaceutical industry. It's a pretty important aspect of our class here, that we have to think about equilibrium, acid-base equilibrium. And that's important in biology. It's important in the pharmaceutical industry. If you go into medicine, you have to think about that when you think about pharmacokinetics and the ability of molecules to cross through membranes and get inside the human body where they belong. We need to be super, super careful about thinking about what we're talking about. If I talk about acidity or pKa, this is going to be super confusing. So here's 3 different nitrogen species that I've got here. And we have to be really careful about the way we describe these different processes. So this type of species that has an N- with alkyl groups or H's on there is called an amide anion. You've seen this before. This is lithium diisopropyl amide. We just haven't drawn the lithium there. So again, I don't call this an amide anion, just I purposely pronounce it in this crazy way. I say amide anion, because I don't want you to think I'm talking about an amide bond. So let me just write this down. An amide anion is just crazily basic, instantaneously and quantitatively deprotonates alpha to carbonyls. alpha to ketones, alpha to esters, alpha to aldehydes. So amide anions are super duper 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 basic. Let me just go ahead and write that down. Super basic. Oh my gosh. That's so much more basic than an alkoxide, like 20 orders of magnitude more basic than an alkoxide anion. Now, if I talk about an amine, this is an amine. That's a world apart from an amide anion with a negative charge. Let me circle that minus charge there. Man, that is a world of difference. It's like 15 orders of magnitude less basic without that negative charge on there. So I'm going to write slightly basic. Triethylamine is probably the most common organic base that we use in synthetic organic chemistry. Dissolves in every organic solvent, and unlike sodium hydroxide, and can pull off protons. Not super aggressively, it's slightly basic. It'll certainly soak up HCl if you're forming an amide bond from an acid chloride. And then the last type of species that we'll talk about, which also has a nitrogen, isn't basic at all. It's an ammonium ion. Onium, right? That tells me that there's a positive charge on there. And this is not basic. It's not, it couldn't possibly act as a base under any conditions that we've ever discussed or ever will discuss. That's just completely inconceivable. There's not even any lone pairs on there. If anything, you you might consider that this is going to donate a proton, and therefore it's a weak acid. If you were to draw an arrow pushing mechanism, that would serve as an acid in an arrow pushing mechanism. And ammonium ions are important. Whenever you take amines and you put them into buffered solutions like human blood, human serum, the cytosol, most of the amino groups that are present at around pH 7.2, 7.4 in the physiological range are going to be protonated under the conditions of the reaction. That's an important, it's important for us to cover that and talk about the expectation for the protonation state of amines. Okay, so before we talk about buffered conditions like blood or biology, I want to talk about what happens if you just dump some chemicals together. And you want to understand, is my thing going to be protonated or deprotonated? How would you predict that? So here's the way you do it. If you've got two reactants and they're in an organic chemistry flask that's not buffered, there's no buffer in there, like carbonate is a buffer in the human blood, for example. So if I take sodium hydroxide and an amine and I want to know, is this really going to be deprotonated to any extent? You pour some molecules into a flask, you got 10 to the 23rd molecules floating around in there. What fraction of those are protonated and what fraction of those are deprotonated? And the way you judge that is you have to know approximately the pKa's of these species. So you would need to know that the pKa for methylamine, is it 35, is it 36? I had to look this up. The actual pKa depends on the species, on how many alkyl groups are attached and what's the structure. Let's just suppose that the pKa is 40. I would normally for an amine, if I didn't know, I would just use 35. It's kind of an easy number. No, it will never, you won't really draw the wrong conclusions if you're using anything in this range. But if I knew the pK for methylamine was 40, and over here on this side, that's the acid. It's donating a proton to hydrogen. How would I know? I just look. It has now lost a proton. That must have been serving as an acid. Then I look at this side of the equation. What's the acid? Well, it must have been the water that was serving as the acid. And if I look up the pK of water, or I just happen to memorize the pK of water, it's something like 16. Now I've got two pKa's. I've got two acids with a certain strength, and I can just subtract them. I can find the difference to find out what's the difference in acidities of these two species. It's 24 orders of magnitude different in acidity. Which is the stronger acid? Well, the one with the lower pKa is the stronger acid. That's really hard to get used to. The lower number, the lower pKa is the stronger acid. It took me decades to get used to that. And you only have a short amount of time. But water is the stronger acid because it has the lower pKa. How much stronger? 10 to the 24 stronger, right? The equation that we use to estimate the equilibrium constant here is 10 to the difference in pKa's, to the power of the difference in pKa's. Even I can do this kind of math. 40 minus 16 is 24. So the equilibrium constant here is KEQ equals 10, and the direction goes backwards, so it's minus 24. It's products minus reactants, so delta pKa, right? If this is the stronger acid, it's pushing it way back in this direction. That means at equilibrium, we would have about 10 to the 24 to 1. Both of these would be, species would be present, and both of these species would be present 10 to the 24. If you put a mole of molecules into a flask of these reactants, you won't even have one out of a mole. There won't even be statistically one molecule of amide anion. Hydroxide anion is not strong enough to deprotonate this particular amine, right? If you had 10 to the 23rd molecules, you wouldn't even on average have one molecule in there that looks like this. And you could have predicted that just by knowing some pKa's. So this is different from buffered conditions. We're going to kind of stop right here, and when we come back, we're going to talk about how to estimate what fraction of your molecules or of your amines are protonated or deprotonated under buffered conditions, and that's that Henderson-Hasselbalch equation that governs that. Henderson-Hasselbalch equation is for buffered conditions where you lock in the pH, but this is where you just dump some stuff into an organic chemistry flask and you let them equilibrate with each other. No buffer. There's no such thing as pH here in this. Well, you don't worry about anything like a concept of pH when you're just dumping stuff into an organic chemistry reaction in a round bottom flask. That's the Henderson-Hasselbalch equation is for biochemistry and biological systems mainly. All right, we're going to go ahead and stop there. Exam on Friday. So stuff like weak nucleophiles adding to ketones and aldehydes, imines, enamines, acetals, hemiacetals, Wittig reaction, acylation reactions and hydrolysis reactions of all kinds. And then finally, an introduction to enolates, that chapter 23 stuff where we're making enolates and we're alkylating them with SN2 reactions. That's the main theme of the enolate stuff. We're not covering aldol stuff. That's chapter 24. We're not covering any of this amine stuff on Friday's exam. Please work the practice exam to get used to the format. If you weren't used to the format of the exam for the last exam, I hope you had worked the practice exam last time. Please work the practice exam to get comfortable with the format of the questions for this online system that we use for taking the tests. I wish we could take paper exams this quarter, but there's no way for us to do that during the campus shutdown or in person. So have a great couple of days and stay sane and stay healthy and stay safe.